And hello, welcome everyone on YouTube. Welcome back to this OpenFoam Salome heat transfer series. So in the last video, we were talking about some instabilities we were having. All right, with a CHT multi-region foam. So just to show you, I'll run this again, and we get this sort of error. This negative initial temperature, blah blah blah. Usually it means that the case has just blown up. You can see the time steps getting smaller and smaller, and the Coulomb number just blows up. Now, why does this happen? Yeah, that's what we are going to discuss in this video. So there are a number of things that can cause instabilities, and it's very kind of difficult to debug because there are lots of factors. Can be the mesh, can be the solver, can be the way you set up your boundary conditions. So now the thing about debugging in CHT multi-region foam is that you practically, especially even in this case, you have a 3-in-1 problem. Alright, why? Because you have 3 sub-regions and all of them are being solved so that you kind of have it's as if there are 3 cases squished into one. So it's a little bit difficult to see which region is actually causing the bug. So I will not debug it here per se. And actually, from experience, I've found that buoyantPimpleFoam is a little bit problematic when it comes to dealing with strange geometries that there are lots of pressure fluctuations or velocity fluctuations. Okay, so that's one thing you got to take note about buoyantPimpleFoam. If it's not a simple pipe case or the Reynolds number is huge, such that you have areas of the case where you have fluctuating velocities. For example, this is a large eddy kind of a simulation. As you can see here, there are some large eddies that are being resolved. Now, buoyantPimpleFoam doesn't always do well in doing that. This actually was generated using buoyantPimpleFoam, and it's a case related to my turbulence modeling series. But case in point, if you have strange geometries like so, like this heat exchanger, where you have this shell and tube, where you have where there are velocity fluctuations, buoyantPimpleFoam doesn't tend to do very well there. So I'm actually going to skip out of this case for a while, and we're going to zoom in on the buoyantPimpleFoam solver, because usually the solid region is not the one that usually causes instability. It's usually the fluid region. Now what is this? Now this is another case using a different heat exchanger geometry, but using a buoyantPimpleFoam. So let me show you what this is like. Alright, so I'll give you this what this case looks like, because again this is a buoyantPimpleFoam case with not so linear geometry, not so simple geometry, and you kind of have pressure fluctuations. So let me show you. Okay, let's see, time varying BC, and I'll go as Salome poly heat exchanger. Now if you know, this is very big. Okay, very good. This is a very big case. Okay, if you know this geometry, this is actually the geometry I was playing with inside my what do you call that, my series in okay, let me exit and reset. Yeah, this is the case I was playing with my OpenFoam intermediate series. So this is a heat exchanger kind of a case. So alright, let me describe this case to you so you roughly know what's going on. Let's see. Yeah, I don't have any time data yet. Okay, CD processor 2, for example. Oh yes, I have a lot of time data here. Okay, so what is this case? Okay, so basically we have a hot side. We have a hot side over here. Okay, so the fluid will flow in from the top here, and you'll go through this bundle of tubes where you'll get heated up, and as it goes to the other side, it's supposed to get cooled down on this side. So it's kind of a loop. It's not like we have a pump there or anything, but it's just that fluid flows in here, gets heated up, and then it cools down and is supposed to be exiting on the other side. Alright, so the first kind of, the most simple fluid to pump through this setup is air. So I've just shown you that this was unstable. Okay, so this is a very unstable geometry, and pumping air through this apparently causes some instabilities. Now how do you kind of visualize what's going on? Okay, basically you want to kind of make your time steps small enough so that you can see the velocity fluctuations to see if it's going out of bounds. Okay, and you want to take a look at the temperature as well, because as you saw just now, the temperature was the one that actually went also negative. Okay, so just to give you some semblance of what this case is about, in terms of temperature, we have just discussed the flow, the rough outline of what's going on. Okay, the entrance temperature here is supposed to be, hold on, yeah, I think this is the cold side. Is this the cold side? Let me check. Cold side tubing is here. Okay, so this is the cold side tubing. Okay, pardon me. So in this setup, the case is such that you have hot fluid flowing in, it gets cooled down in this bundle of tubes and then gets heated up. Now how hot is this fluid when it comes in? It's supposed to be 500 Kelvin. Then when it flows through these tubes, it's supposed to be cooled down to a temperature of, let me see, vi0.0/T, and I'll go all the way to the bottom. Okay, so it's supposed to be an inlet. It's going at 500 Kelvin. The cold side tubing is supposed to be 293. Okay, it's not 300, it's 293 Kelvin. And then it has, the kappa layers and everything. We talked about external wall heat flux temperature briefly before. Okay, that's what I actually use for my outermost part of the shell, using that as a boundary condition, as I kind of discussed in the last few videos. Not only do I have a cold side tubing with a kappa of 385, this is a thermal conductivity. Alright, this is a kappa of 385. I also have insulated tubing. So the insulated tubing will have a thickness of, again, roughly give or take 2 cm, whereas this one is 2 mm, like the copper tubing itself. This insulation tubing is supposed to be about 2 cm thick, and we'll give it a kappa of 0.04. As again, we saw the typical value. And for the heater side, I just changed the mode to power, and the input power is about 80 watts. Okay. Alright, so this is our case setup. So how do you see the data? Again, I was saying, to help you see, there are a few things you can do. You can actually make your time step very small, so that roughly around this 1 times 10 to the minus 3, you just adjust it so that you can see the evolution of the temperature and the velocity, and then you can see, at which point, which time step, and which rough place, the area, the place in which, which part of this geometry does the flow become so-called unstable, numerically speaking. So there are a few things you need to do. You need to make sure your time step is small enough so you can observe and monitor what's going on in your case, what the velocities and temperatures are like, because this is usually it helps you to see where the instabilities, the unstable regions are. Okay, and if you go to system, okay, and I'll go to control dig, there's another very good function object. It's called the current number function object. It will help you to monitor the current number of the case, so that you remember when we had our case, we have our PimpleFoam case or buoyantPimpleFoam case. It will show us the maximum and minimum current number. So if you want to know where this maximum and maximum current number is, you can use this current number function object. So you can just put it under functions in control dictionary. It will use this thing current test, and then it will give you the current number. You need to type in the library as field function objects. The field you want to measure the current number with is the phi field, which is actually row times u. So that actually gives you the phi field, and it will print out a current number field. So where is this current number field? It will be printed alongside your in your timestamp directories. So you will see what I mean shortly. So you will need to give it an enable and a log, and then execute and write control. I will just say it is write time. That means every time you write new data, your temperature data, your velocity data, you will also write the current number. So that is a very convenient thing for you to monitor where the case is in terms of stability. So I'm going to run a reconstruct path first, so that I will have all the relevant fields for having our data. For our data. So it should be running. So let me press F5 first, and it will give you sort of a rough feel. Okay, it'll give you sort of a rough feel where things are going. So this is the data. As you can see, the velocity is kind of steadily changing, and you can see, especially towards the end, the velocity suddenly becomes, like reddish color. So something is of course going on. And of course, if you want to see what's going on inside, you can always look here. Use the slice plot. Use the whatever plot is comfortable for you. I use the Z plane, and I'll unclick the show plane so that you can see, this is what the pressure profile is like. You can take a look at the velocity and temperature. So you can see the air is going in here. All right. Okay, let's go back to the start. So air is supposed to go in from this part. Okay, and apparently at the beginning there is some part that it's red color. Why is it red color? So you can take a look at the initial conditions. Okay, you can take a look at the initial conditions. So let's go to 0 and let's see the velocity u. Okay, you can see that the boundary, all your initial velocity has it will be given as this vector here. It has a z velocity of 0.1. That's why you have suddenly there's some initial velocity here, and it's like as if all the air inside this tube is like going in the positive z direction, and it suddenly hits against the wall. Okay, so that's a bit of a unphysical thing, but usually after a while the solver will take care of it, and this velocity will just dissipate. Okay, so you see this velocity here. Yep, it will initially have an increased velocity like that, and then after that it will just kind of die down. Okay, so let's load up the full time. Okay, I'll press F5 again. Yes, okay, good. Let's load up everything, and let's see where is the so-called problematic area. Now you can see that this part, as it's going in, okay, as this fluid is going in closer to here you'll see some sort of red spots that are forming. Okay, you can see there are lots of red spots here that are forming. So this is something pretty interesting to look at. And if you take a look, of course, at the temperature field, okay, remember we are supposed to come, the temperature is supposed to be, you know, like 500 Kelvin, so to speak, 500 Kelvin. And then well, now that the fluid is going in, suddenly there are parts of the fluid that become 600 Kelvin. Could it be because of a slowdown, or maybe it's the solver instability? Well, these are the things we also have to, you know, take a closer look at. So what I want to kind of zoom in on is this temperature field. Okay, this temperature field. Okay, temperature field is over here. We can do a rescaling of this. You can see the maximum temperature is 629, and the minimum temperature is 190 Kelvin. Okay, so this is actually such that the temperature becomes a sub-zero. So this is a highly unusual. So and usually, in a thermodynamic sense, the only way that the air can go to such low pressures is that, such low temperatures, is if suddenly the air is allowed to do lots of work against something. That means the air is expanding and the pressure is dropping, and then your temperature will fall. Now you have something, and usually we call that the Joule-Thomson effect. But now we see this. Usually when air is flowing through something, you don't see the temperature actually going all the way down towards 190 Kelvin. That's minus 80 degrees C, and this just doesn't make sense. So obviously something here is amiss. So let's scale this color map. Remember, the lowest temperature is supposed to be 293, and the highest temperature is supposed to be 500. So you can see that over here, the 500 part is over here, in the beginning, and then of course as it mixes with the fluid here, then it starts to disperse. So if you want to see the parts that are going above 500, then you can use this trick. Okay, because now the parts that are 500, they are red colored. Now I just want anything maybe above 500, for example 530 or 550. I want that to be red colored. So let me rescale by changing the maximum temperature. Let me change the scale such that, okay, your temperature here, okay, the temperature here is such that anything above 550 Kelvin is going to be red colored. So what are we seeing here? Okay, try to visualize. Okay, so air is flowing into this heat exchanger, but somehow over here, for some reason, there is some temperature increase. Now what's the reason for possible temperature increase? Thermodynamically speaking, it's probably because the pressure at that region suddenly increases and does work on the air. Okay, so let's take a look at Prgh. Now Prgh tells a different story. Can you see that the pressure here, we don't really have any localized spots of high pressure. So that's something amiss. So from this we can kind of think, normally when you compress air, the temperature will increase, but what we are seeing here is that all these parts are labeled red. This is Prgh. This is pressure without the hydrostatic component. And if I include the hydrostatic component there, you'll see that the pressure profile is more or less the same. So we can see that the problem that's causing this, it's because suddenly I guess when you take a look at the air is coming from a very even geometry like a cylinder, and suddenly it's going into this top part of the heat exchanger, which is a sphere, and then something wonky goes on with the solver, and suddenly the temperature goes very wonky. Okay, so now you can see that in action. Alright, So let me repeat again. You can see some hot air going into a cold medium, and we see a temperature rise from 500 Kelvin, which is the inlet temperature, and that's supposed to be the highest temperature of this whole system, because the other parts of the system, they're supposed to be 293 Kelvin, 300 Kelvin. Now one possible reason for this temperature increase is a pressure increase, but if we take a look at the pressure here, we don't see small spots where you have very high pressure localized in the system. So we must the other possible reason is, of course, numerical instability, and that's probably what's causing all these funny spots. Okay, and so we can actually see that, okay, maybe something is going on with the numerical instability. So where is its instability coming from? Okay, time is up, so let me quickly finish, and then I'll continue on in the next video. Okay, so anyway, so this is showing that the weird geometry is causing some kind of fluctuation in temperature. So that's the temperature field, and we can see stuff that's going on here. Okay, the other one we want to see are the Courant number fields. So you can see under the data, you can go to Courant number fields, and that's why we have our Courant number generator, or Courant number function. Okay, so this is at time equals 0.037. Okay, so let's rescale. Okay, so you can see the Courant number, all of these Courant numbers are basically pretty okay, except, I mean, if you take a look at how small or how big this Courant number is here, you can see that the average Courant number, maybe for most of the pipe, this Courant number is 0.1. Then you have spots where the Courant number is much higher. For example, you can see all these red spots over here and over here. So you know that something is going on over there. So you can roughly guess the area. Okay, where are your problem areas in this simulation? Okay, and lastly, of course, we look at our velocity, and again we see that somehow the velocity magnitude here is very high. Okay, normally speaking, if we have fluid from a smaller pipe, smaller cross-section area going into a place with a larger cross-section area, we expect the velocity to decrease, right? I mean, that's for mostly incompressible flow. Okay, and we can see that the velocity magnitude is about 6.2 meters a second, the maximum one here. And air is compressible, yes, but the only place where we have to start taking into account these compressibility effects is over a Mach number of 0.3. So speed of sound for air is about 330 meters a second. Compressibility effects will be Mach 0.3, which is about 100 meters a second. This is far below 100 meters a second, so we should not see too much compressibility effects here. So we can treat this fluid pretty much incompressible, and we see that as we are going from the thin pipe to somewhere thicker, we see velocity increase. So somewhere around here is where our case is going wrong, and we see actually we have to make another observation. We make another observation. If you actually go and look at my intermediate playlist, you will see that the geometry of this sort does not cause problems in PimpleFoam at all. So somewhere between PimpleFoam and buoyantPimpleFoam, there's some adding all these energy equations and compressibility solvers, because buoyantPimpleFoam does solve for compressible flow as well. Somewhere there is a problem that is starting. So this is like the first part of diagnosis of where your problems are. So you can see, like, for strange geometry such as this, you will see sudden increases in velocity and sudden increases in temperature without the corresponding increases in pressure. So you know this is sort of numerical instability. So how can we then apply this back to our CHT multi-region foam? We see that in our shell and tube heat exchanger, normally the shell region is where we have, again, very strange so-called not strange geometry where the velocity makes abrupt changes, right? Where the shape changes suddenly, like you see here. Okay, the shape changes suddenly, and therefore the velocity and temperature and pressure suddenly will change. So this is going to cause numerical instability. Why does it happen? Okay, so we'll continue that in the next video. Thanks for watching.